Welcome to topic 1 of computer programming. And in this topic, there are 3 subtopics. Okay. Now, those subtopics are number 1, types of language, number 2, programming constructs, and number 3, computational thinking. Okay, so starting to think computationally. Now, first of all, types of language. Okay, so when we think about the different types of language, we can use a couple of categories. Okay, and for this particular unit, we need to know about low-level languages. Now, low-level languages are a programming language that provides little or no abstraction from a computer's instruction set architecture. So commands or functions in the low-level language map very closely to the processor's instructions. Now, in most cases, a low-level language refers to machine code or assembly language, and the word low just means that there's a small or non-existent amount of abstraction or amount of distance between the language and machine language. Okay, and low-level languages are sometimes described as being close to the hardware. Okay, so when we have a look here, all right, here we have this graphic that I found online. It shows quite a good illustration of the two. Okay, we have high-level languages, and that would include Python. Okay, C. We've got Fortran, which is quite an old language, and more importantly, we have the low-level languages down at the bottom here. Okay, so down here we have assembly language and machine language, and here is our hardware at the bottom there. Okay, now these machine languages are often written in like a byte code of zeros and ones. Okay, whereas these languages, the high level languages, are often written with English words. Okay, like print and list, copy, things like that. Okay, commands that we can understand. So some common uses for languages. JavaScript is often used for front-end web development. So every browser can interpret JavaScript, okay? And JavaScript is the language of the web browser. And it can be used for applications as well, but traditionally it's a web development language. So back-end web development, what goes on behind a web service, it can be things like Java, PHP, C#, and Python as well. Python can also fit into this desktop application. Python can also be used for scripts. So Python is a general purpose language. Okay. Now, we have games development. It can be done with C++ or C# typically. You can make games with Python, but that's not really the most common use of it. Mobile application development, we have Swift, Java, C#, and I've added a link there that'll make that available to you at a list. So here's a little kind of chart. Now, these change all the time. These change all the time, but most likely C and Java are the most common programming languages. Okay, and then just above that we have Python. Okay, now Python and C and Java are always the top 3 programming languages at the moment, in the last few years anyway. And above that, we have these Microsoft languages like C#, Visual Basic. Then we have JavaScript. Then we have other kind of more specialist languages, SQL, Ruby, Go, Perl, R, things that are more specific. Okay, so the language that we're going to learn in this course is going to be Python. And the good thing about Python is understood to be very easy to learn. So let's look at some programming constructs now. So what actually is a programming construct. So when we construct a program, okay, we can consider that the program can be built from a predefined set of primitive instructions. Okay, primitive instructions just mean instructions that are already built in to the computer. So things like add, to add two numbers together. If we had to write out the program to add two numbers together, um, and other things like that, it would make a programming language more difficult to use. So generally we start off with some primitive instructions, and we can put these primitive instructions together to form calculations, okay? And once we've created our set of instructions, once we've put them together, when we run it, the program will be interpreted line by line by the machine. So having a look at the machine's architecture here, inside a machine, this is a very simple kind of theoretical overview of a machine. So we have the memory up here, the RAM, then inside the processor, okay, we're going to have a control unit and an arithmetic logic unit. Now the program counter keeps track of where we are in the program, and the arithmetic logic unit performs calculations, okay, and passes these back and forth into and out of the memory, okay? Now, when we run a program, the computer will create a set of instructions in the memory, and then the ALU will run those instructions, perform those calculations, and the control unit will keep track of where we are in the actual program. Okay, so that's in its most simple form. That's a basic layout of a machine. So what is the program counter? So when we run a program, the interpreter goes to the first instruction. So you can think of a program as similar to a program if you went out to the theatre or went to see a show. You might buy a little booklet, and inside the booklet would be a program. And the program would tell you the time, like let's say first act of the play or first part of the show will start at this time. Then something will happen. Then there will be an interval, let's say 8 o'clock. So a computer program is not too dissimilar from that. Okay, we have the program counter will read the first instruction, and then it'll execute it. Then it'll move to the next instruction. The program counter increases by 1. The next instruction is executed. We'll take some values, run them through the ALU, do the computation, store the result, and the computer will just keep doing that until it gets to the end of the program, okay, until the program's finished, and that's the end. So the program counter just keeps track of where we are. Okay, so every once in a while we're running through this set of instructions line by line, working our way down, the computer will get to an instruction that's a test, okay, and it'll say, hang on, stop running, stop this line by line running. What I want you to do is I want you to check something. Now, I want you to check if a number is greater than 0. I want you to check if something exists. I want you to do something, okay? Now, if that test turns out to be true, this may change the program counter, okay? It might say, okay, if that's true, don't do line 3, do line 6, okay? So this is how we can change where we are, okay? And apart from that, that's really all the computer does. Okay, so in summary, we have a control unit that helps us follow through a sequence of instructions, and we're going to see very shortly in this course how to start building up programs to do exactly that. Okay, so just going to move forward to the next topic, which is computational thinking. Okay, so thinking computationally, what does that actually mean? Okay, what does it mean to think computationally? Well, okay, let's have a look at some examples. So fundamentally, a computer can only perform two tasks. Okay, a computer can only do two things. And those two things are, number one, perform a calculation. Okay, and number two, store the result. All right, so the computer just does these things very quickly. Okay, that's all the computer does. Performs a calculation and it stores the result. Okay, so computational thinking means to, when you're faced with an interesting problem or challenge, can you break that problem down into a set of steps that will allow you to solve the problem? Okay, that's what it means to think computationally. Okay, so sometimes when we think computationally, we need to think of algorithms, right? What's an algorithm? So an algorithm is an idea. Okay, and the best way to think about an algorithm is it's like a recipe. Okay, so if you open a cookery book of recipes, you could call that a book of algorithms. Okay, it's an algorithm to show you how to make cakes or show you how to make some different types of bread. Okay, those are algorithms in some way. We wouldn't call them algorithms, we would call them recipes, but it's the same idea. So an algorithm is an idea or a set of steps that you can work through. Okay, and a computer program is an interpretation of an algorithm written into a computer. Okay, so some problems are just too difficult for computers, such as predicting the weather on a very local scale. It's just too complicated for computers. Okay, but very simple problems, if we can break them down into steps, then we can teach that to the computer, and the computer can work it out for us. And you'll often hear a phrase out there of, oh, well, let's ask, Bob, because Bob understands computers. And I don't think that's particularly true. I think you should try and think of it the other way around. It should be, well, let's ask Bob because computers understand him. Okay, it's not that you understand computers, it's that computers understand you, if you see what I mean. So here's a really simple algorithm. This is how to get to work. Okay, so the first thing we do, right, is we begin. Now, what does begin mean? It just means start. Start thinking, okay? Line one. Okay, do you work in walking distance from home? Now, if you have to make a decision, we put this inside a diamond shape. Okay, so do you work walking? Do you walk? Can you walk to your work? If you can't, if you can, then that's the end. Okay, done. However, if you cannot, then think, well, do you have a car? If you've got a car, drive to work. The end. Okay, if you don't have a car, you can use public transport. You can get the bus. Okay, the end. So that is a simple algorithm about getting to work. Okay, that's all it is. It's nothing complicated. It's just a series of steps that you can follow, and in there's some decisions, yes or no. Okay, and this way of writing something out, this is called a flow chart here. Okay, so one more question to ask today, and that question is, what is knowledge? Okay, so if we want to understand what it means to think computationally, okay, that leads to another question. What actually is computation? Okay, what is computation? And that leads to another question, to think, well, what's knowledge? What do we know? Because if we're going to try and work something out, we need to know what it is first, what it is we're working out. And when we think about knowledge or knowing things, that can actually be broken into two categories. Okay, so there are two types of knowledge. Okay, the first type of knowledge is called declarative knowledge. And declarative knowledge is statements of fact. Okay, and the second type of knowledge is called imperative knowledge. And imperative knowledge is how-to methods. Okay, so let's think about this. Okay, if I told you that there is a bag of tools on the floor, okay, all different types of screwdrivers and electrical test equipment, okay, that's declarative knowledge. You know what a screwdriver is, okay, you know what a piece of wire is, right? You know what a pair of pliers are. You know those facts, okay, but that doesn't mean that you have the imperative knowledge to change a fuse box in a house, unless you happen to be an electrician and you're studying this course and you're also an electrician. If that's the case, then you have both the knowledge of fact, what a fuse box is, what a screwdriver is, and you also know how to put those things together to make it work. Okay? So those are the two different types of knowledge there are. So if I said to you, you know, I want you to go and I want you to make me a cup of tea, I accept that we've got some primitive instructions in there. You know what tea is, you know what a cup is, okay? You're familiar with the concept of a cup of tea, okay? So if you've got that declarative knowledge, if you know those facts, then I will also assume that you have the imperative knowledge or the methods, you know the steps in carrying out the process as well. Okay, so I'm going to look at an example of these two different types of knowledge. So here's an imperative example of how-to knowledge, okay, a method or a recipe for finding something. Now, this is an algorithm or a recipe for working out square roots, okay, and this is attributed to Heron of Alexandria. Now, there's some debate as to whether or not this was actually Heron of Alexandria. Heron of Alexandria lived in the 1st century AD. Okay, I think that's called ACE now, after the Common Era. They called it AD when I was at school, so apologies if that's wrong. So this method will allow us, this Babylonian method will allow us to work out a square root of a number. Okay, and by doing this, we follow through a series of steps. Now, we need to start with a guess called G. Okay, if G times G is close enough to X, and X is what we're trying to work out the square root of, then stop. That's the answer. So let's say we are trying to work out the square root of 25. If G, we guess that G is 5, 5 times 5 is 25, stop. Okay, now if we guessed 4, 4 times 4 is 16. It's not 25. So we need to do something else. And what we do is we're going to average G and X divided by G to give us a new guess. Then we're going to times the new G by the new G, and we'll repeat the process until we get close enough. Now I'll show you this example in a minute. Now that's imperative knowledge, okay? That's a series of how-to steps to work out a square root. But the problem with that is that doesn't tell us how to find that guess. Okay, I just told you we could guess that it was 5, and you didn't think anything of it. You said, oh yeah, fair enough, guess it's 5. But the computer can't do that. Okay? A computer needs some sort of declarative knowledge. You can't say to the computer, go and guess a number for me. Okay, you need to tell. Now, there are programs that will give you a random-ish number out. Okay, but really the computer can't just guess something like a person can. Okay, so sometimes we need some declarative knowledge. We need to give it something. Now, you could easily just say to it, always make the first guess 1 and then work out from there. The computer would be like, fine, guess is always 1. But that's still declarative knowledge. You've still declared that guess, okay? You haven't given it a how-to method to find the guess. I've opened up a calculator here, and let's try and guess a number. So I'll just grab my notepad as well, make sure that I don't mess this up, keep a note of the steps. So let's say we're going to guess the square root of 64. Okay, so to guess the square root of 64, SQRT 64. Now, we all know that the square root of 64 is 8. 8 times 8 is 64. Okay, so that's that. We already know that. But in order to show you how to use this algorithm, I'm going to take a different guess. Okay, we're going to guess that the square root of 64 is 6. So let's do 6 times 6, and that gives us 36. So looking over at the algorithm here, if g times g does not equal x, so x is 64, okay, then what do we do? Okay, g times g is 36. So it's wrong. So we need to follow this step down here. Now I've written it out in kind of pseudocode here. This is a sort of pseudo notation. Okay, so what do? We take g and we add it to x divided by g and then average the two together. So let's work out the brackets first. Let's work out inside here first, okay? So x divided by g. So x is 64 divided by g, and the first g was 6. 64 divided by 6 gives us 10.6. So 10.666667. Right. So we've worked out this little bit in the brackets here. Now we're going to add that to g. Okay, so add that to 6, and that gives us 16.6667. Okay, 16.666. Now we need to then do this here, average of these two. So x divided by g plus g over 2. So divide that by 2, and that gives us 8.3. Okay, 8.3. So 8.3 is the new g. So g equals 8.3. Okay, we'll ignore the 333. We'll do it to 2. We'll call it 8.33. So that's the new g. So if I times that by 8.3333, something like that, g times g, we'll see if this equals x. Okay, 69.4. Okay, so that's g times g is not x, but we're getting closer. So if we know that that's not x, let's go back to our guess here. Okay, and what we're going to do, okay, is run through this again down here. So the first step to do is x divided by g. So let's do the new g is 8.3. So let's do 64 divided by 8.3. Okay, what's that going to give us? 7.68. 7.68. Then what we're going to do is add that to the new g. So that's 8.33333. Okay, so add the two of them together. That gives us this number. And then what we need to do is average those. So divide that by 2. Divide it by 2. And that gives us 8.00. 8.00. Now if we chop off, if we leave it at 2 decimal places, times that by 8.00, that gives us 64. And 64 is x, and that is the number we're looking for. And so that means that the square root of 64 is 8. And we've used Heron's algorithm to calculate that. Now, a little bit of a simple method when we're working out for 64, but this will work for giant numbers as well. Okay, so that is an algorithm that we've just followed through to work out the square root, Heron's algorithm of the square root. So this is lab 1 for computer programming. Download this document from the Moodle, fill out the fundamental tasks, the knowledge, and then based on what we just saw there, we're going to try writing out an algorithm for crossing a road here, okay, using numbered steps. All right, then once we've done that, we're going to use how to calculate the square root of a number. We're going to write out a little algorithm here to solve these three. Now, it says here that we learned how a guess and check algorithm works. A guess and check algorithm is exactly what it says on the tin, basically, exactly what that says. A guess and check algorithm literally means you take a guess and you check if it's right. Okay. So a very common way to think about a guess and check algorithm would be if we were to play a game of guess the number. So if I said to you, can you think of a number between 1 and 10? I'm thinking of a number between 1 and 10. Can you guess it? You'd probably say something like 5. And I would say that's too high. So you've taken a guess, you're checking if it's right. If it's not, you're going to try something else. Okay, if I said it was too high, then you're going to go lower, aren't you? You're probably going to say 2 or 3. And if I said 3 is too low, then you're going to guess 4. And you've used a guess and check algorithm. You probably never called it that before, but you've always known what a guess and check algorithm was.